present himself.
Okay. Hello, everyone. So my name is Victor Kos. I'm a third-year PhD student at the Université Paris-Ouest, Nanterre-La Défense, and also have IFP, Énergie Nouvelle, and Chaire Économie du Climat, so all in Paris. So first of all, I would like to thank the organizing committee for inviting me. So yesterday, Charles Halls gave an overview of the EROI, of the concept, of the history. And what I'm going to present today is a paper I've written with Florian Fizen, where basically the question we ask is, what is the global trend of the EROI of coal, oil, and gas from the beginning of their production to present? So we are not really interested in what was the value of the EROI of oil in 1930 or in 1945. What we are interested in is the trend, okay? Not the precise value for a given year. And so, for example, I put these two pictures because it shows how coal was mined in the 1900s and how coal is mined now in 2000. For the record, the two, I don't know if you're familiar with this kind of monster. The two dots here are people. So it gives you an idea of the size of the excavator who is mining lignite in Germany in this picture. So of course, to do that, to estimate the EROI of coal, oil, and gas from the beginning of the production to present, we did not use the same methodology as what was presented yesterday for PV, okay? Because doing so would require to do the same work for every year or every 20 years during 200 years. So it will be a lot of work and a lot of data to collect. So we have used another methodology. So first of all, about the introduction, Kare King, who will present after me this morning, he made 3 recent papers. I'm sorry, Kare, if I spoil your presentation, but he made 3 really interesting papers a few months ago, where he explained big differences that was not clear for people working on the EROI so far. So he makes the difference between calculating an EROI on a full life cycle project, like for PV yesterday. Okay, this is a clear energy return ratio, and the difference between the ratio of annual flows, energy produced, divided by energy input as annual flows, which in this case is more a power return ratio and not an energy return ratio. So there is difference between calculating an EROI for a precise project for which you know the lifetime of the project, like yesterday for the PV, and trying to estimate the EROI time series, so the evolution of the EROI of a given production system, energy system, over time. So EROI time series have been computed mostly for fossil fuels, okay, for American oil and gas, Canadian oil and gas, Chinese coal and oil. But mostly they are what Kare King call gross power ratio, because they are based on financial data of outputs, yearly output divided by yearly input. And the only very long time study is for Guilford and al., who have assessed the EROI of the American petroleum from 1919 to 2007. And all the other studies, this is the study with the largest time frame. All other studies assessing the EROI of coal or oil in different countries, they go back to a few decades at most. So basically where you have data, so 1980 or something like that, okay? And they also, as you might know, or as Charles Hall told yesterday, that the EROI of fossil fuels is declining, okay, on the last decades. But what we ask is, it has been so often postulated that the EROI of fossil fuels was really high in the beginning of the production. So sometimes you hear that the EROI of oil was above 100 at the beginning of the production, but there is no real calculation to be sure that this was the case. Something for coal, something for oil. Yes?
I'm responsible for that error.
Okay.
Okay, and I'd also like to say I'm one of the officers, Guilford et al., and we've got no one, I don't know, really my students. So, the reason, oh, do I need this? The reason for the erroneous 100 to 1 was that it was published by Cleveland, also one of my students.
Yeah.
And it is for, but he didn't make it clear in his 1995, whatever.
1995,
yeah. Speak into it? Oh, good Lord. Okay, so, try to lower my voice. So the reason is that that was for finding,
yeah.
not producing. I don't believe the EROI for producing oil in the U.S. Was ever above about 30 to 1. And in the Guilford et al. Paper, we, with the help of Jean Leraire, we got, for finding, it was as much as 1,000 to 1 back in 1919. But the 100 to 1 is not true.
Yeah. So it's
for producing.
Yeah. But unfortunately, it's a number that appears in some papers, and there is no calculation, so people tend to think it comes from a real calculation. So that's just my point.
The highest I've ever seen is around 50 to 1 in Norway.
Okay. So this is the first question. So what was the EROI? Can we calculate it really far in the past? And I'm also interested about the global scale, okay? And the only study about oil and gas at global scale is Gagnon et al., who have investigated the EROI of oil and gas from 1992 to 2006, okay? But so before that, we don't know. So is it possible to go back to 1890, so the beginning of gas production? Not the beginning, but the beginning of reported gas production for which we have data of the quantity produced each year. Same thing for beginning of oil production, 1860, beginning of coal, 1800s. Well, coal was known for antiquity, okay, but we have numbers about the quantity produced from 1800s. And okay, so I'm gonna show you the methodology and then the results we have for this price-based estimate, because in fact we have relied on prices. And then what another question I will ask is that they all have proposed a theoretical model of the EROI with just a simple equation. And this theoretical model of the EROI has never been calibrated on calculated EROI estimates. So I was wondering, is it possible that the theoretical model reproduce estimates of EROI time series? So this is another question I will try to answer. So to estimate the EROI of coal, oil, and gas from the beginning of production to present, we have relied on a price-based approach inspired by the work of King and al., who proposed a relation between the energy price and the EROI. And so we're going to use that. So for a bit of system boundary, there is different EROI you can calculate. Basically, there is two dimensions in the EROI. The dimension of the output. So where are you in the energy system? Are you at the mine mouth or wellhead? So are you extracting primary energy? Or are you at the end of a power plant? So in this case, the output is electricity, and you speak about final energy. So this is the output boundary. So our EROI is about primary energy. So this is what there is the one here. And what is the boundary of the input? So, and you saw yesterday that for PV, Pedro went really far in the boundary for the inputs, okay? Because we rely on prices, we think the prices of a given energy, okay, be it coal, oil, and gas, is supposed to cover the direct energy invested to extract the oil or the coal, the embodied energy in the physical capital, and in the price, you also have the wages paid to workers in order to sustain their living, so in order for them to have food, shelter, and transport. So the system boundary of our EROI is E1 labor according to the nomenclature of Murphy-Earl. Okay, so price-based estimate. So what we say is that the yearly EROI of any fossil energy sector, G being coal, oil, gas, or all fossil fuels, is basically the amount extracted for a given year. So this is calculation for each year, okay? I dropped the time index for convenience. So for each year, the EROI is the energy out divided by all the energy that has been invested in the energy system, okay? But we know E out, okay, because we have quite reliable databases about how much coal, oil, and gas has been extracted. We don't know how much energy has been invested, okay? So basically, we say that E in, okay, the energy invested is basically the amount of money invested in a given year time the energy intensity, so how much energy has been consumed to produce the dollar that is invested in the sector, okay? So basically now the equation is this one. So now you have to evaluate the quantity of money invested in each sector every year, and how much energy does it cost to produce these dollars invested. So now we make another hypothesis that basically the money invested in a given sector is supposed to cover a levelized cost of energy per output unit, okay, LCOE, times the quantity of output energy. Okay, so the total quantity of money invested in a given energy sector for a year is basically the cost per unit of energy extracted times the number of units extracted, okay? And this cost is broadly, roughly speaking, supposed to be the price divided by the monetary return on investment, which is in fact the gross margin of the sector. Okay, basically what you expect is that the price will cover your costs. And the producer wants to have a margin, okay? So this is the MROI, the gross margin. This is just an estimation, okay? It's just, I know that reality does not work like that, but this is the way we have, this is the only way we have found to estimate the EROI far in the past, okay? So now to estimate the EROI, what we will need is prices series, okay? So the variation of the prices over time. The variation of the gross margin of each sector over time, and the evolution of the energy intensity of dollar invested in each sector.
What do you call the gross margin?
Well, basically it will be price minus cost, okay, roughly speaking. So for this one, we have some data. The two of us, we don't have really good data. So what we do in the first approximation, and after that I will show sensitivity analysis, is that we say that, in fact, the energy intensity, we will just take the energy intensity of the global economy. Okay. In fact, the energy sector are more capital intensive than the average energy intensity. So by making this hypothesis, we underestimate the energy intensity. So we overestimate the EROI. Okay. So basically, the energy intensity of the economy, it's simple. It's for a given year, all the energy you extract divided by the global GDP. because we are at the global scale. And for the MRI, we will also suppose that all sectors have the same MRI. Okay, and I'll show after that how we have estimated the MRI, so the gross margin of the fossil sectors. And we can also do that, so G will be coal, oil, and gas, and we also do that for all fossil fuels, okay, by just making an average price of fossil fuels weighted by the different quantities. Okay, so the average price of fossil energy is basically, it's a quantity-weighted price of all the other energy. So there is a mistake here because G should be G different of all fossil fuels. Okay, here you just have coal, oil, and gas. So how do we estimate the prices? So we have good time series of prices for coal, oil, and gas in the US, and not really at the global scale. Okay. So we retrieve this data for coal, oil, and gas in the US in different units. Okay, nominal dollars per ton for the coal, $29 per barrel for oil, nominal dollar per 1,000 cubic feet for gas. We made some conversion, and we expressed all prices in $1990 for constant dollars per terajoule, okay, per the same energy unit. So this is the American price, and we are making another huge hypothesis: is that these American prices are good proxies of global prices, which is kind of good hypothesis for oil. For gas, little less, and for coal, it's a really bad hypothesis because, of course, coal is mainly, there is no real international market for coal. You have regional markets, okay? So the price can be really different in different places because the cost of transport is really high, okay? So we should have computed a real average price of coal with if we knew different prices in different regions over time. And there is another hypothesis is that the coal here has the same quality, which is of course not true because you have different, really different quality for coal from anthracite, from lignite to anthracite. Okay, the energy density is not the same at all. Okay. Energy intensity. Quite easy. So we just retrieve the gross world product of Madison, this curve, okay? And the primary energy production retrieved from the Shift project, so thanks to the team of the Shift project here. Here, for the different energy sources, okay? And we had the estimate of traditional biomass, okay? So wood and crop residues from Fernandez, et al. And Smil. It's this curve, okay? So this is wood and crop residues, okay? And if you make the sum of all primary energy divided by the global world product, you have the energy intensity of the economy. Okay, so basically what it means is that to produce $1 in 1800s, you will need 30 megajoule. The economy will need 30 megajoule. And currently, it's just about 10. Okay, so the energy intensity of the global economy has been decreasing a lot. And we just show something that we have seen in studies where when you omit traditional biomass. If you forgot that at that time there was a lot of wood and a lot of crop residues, you think that the energy intensity was really low. And it's something we have seen in studies. So I just put it there to see the difference. So now the last variable that we need to estimate, the MRI, so the monetary return on investment of the fossil sectors. So we follow Damodaran, who claims that the US fossil energy sector MRI, roughly speaking, follow the US long-term interest rate, okay, that we have retrieved from Officer, with a 10% risk premium, okay? Another big hypothesis. And I will show after that sensitivity analysis about this hypothesis. So this is the long-term interest rate in the US. So this is the MRI that we compute, okay? And we show what is the MY of 1.1 that is used a lot in other EROI studies. Okay, so we just show the differences. And that's it for computing our price-based estimate of the EROI. Okay, so this is the main result. Okay, EROI of coal in black. So which is on a basically increasing trend. EROI of oil being here in gray, who has a maximum around here, around the 1930s, and with a declining trend after the 1940s, but mostly increasing before. And for gas, same thing, but EROI of gas goes really high, up to 200, okay, before declining. So this is our estimation on the price-based methodology of the global EROI of coal, oil, and gas. And fossil fuels, if you aggregate all fossil fuels, of course, the EROI of all fossil fuels follow the one of coal at the beginning because coal takes the largest share of fossil fuel production. Okay, it's just here. And then it is more following the EROI of oil because, yes?
So the gas is gas feed or gas that you get when you extract oil?
Good point.
What share of the
Yeah.
gas?
That's something that's a problem of another problem of our methodology, because, as you know, there is a lot of combined extraction of oil and gas.
So what is the cost?
Yeah, and yeah, we did not find a way to make the difference. Okay, so this is basically it's like if gas was extracted in separate field and oil in separate field, basically. Which Charles Hall has said in numbers of papers that the gas has helped having a quite high EROI for oil. And if you remove gas, maybe surely the EROI of oil will be lower, in fact.
Can you point which is oil at the last data points? Which is oil, which is gas?
Oil is this one. Gas is this one. And coal is there. I will show after that separate figures, okay? And comparison with other studies.
May I recommend colors to you?
Colors? Okay. I like black and white.
Victor,
Yeah. Yeah.
this sharp fluctuation, I suppose, reflect fluctuation in the prices, but not in the physical quantities, not in joules.
Right. So it means that
Is
the
there a
real
way
physical
to,
EROI follows this trend, but with less volatility. Okay? I will speak about that just after. But yes, it's a good point.
But what happens with gas 1910 or 1950 when it suddenly goes up? Is this new technology or price development?
There?
No, 19. Is this virtual one?
There?
Yes. No, just this step. This is a little step. Why does it
Just there?
Okay, now.
There?
Why does it jump?
That's the estimate. I mean,
Yeah, is this in a denominator or a numerator? And what is the factor?
I will show sensitivity analysis just right now.
It's Texas.
Okay?
Texas.
Texas or Texas?
Texas. Texas. So in the first methodology, we just try one MRI. So we try two of us, okay? This one is simple, okay? We assume MRI is constant, so the gross margin of the energy sector, fossil sector is constant. And for variant B, what we have tried to do is reconstruct what is called the Neisser Arca Oil Index, which was previously the Amel Oil Index, which is a price-weighted index of the leading companies involved in the exploration, production, and development of petroleum. Okay? So basically, it's supposed to measure the performance of oil companies. Okay? But this index exists only for 1984 to 2009. Okay, just there. Okay, and it can go. It doesn't exist previously. So what we did is that we took the Neisser data that exists up to 1815. Okay, and with some really simple econometrics, we made an estimation of the Amel Oil Index, a correlation with the Neisser data. So we have the Neisser data in the past, and we just recreate the Amel Oil Index. So this gives you the 3 MRI we test. So this one is the first MRI following the US long-term interest rate. This one is the constant one, 1.1. And this one is the one we have recreated. So it means that for some year, companies are losing money. Okay? When you have an MRI of 0.8, it means that the price is not covering the cost and you're losing money. But it can happen sometimes. Okay? The fossil fuels companies are not winning every year. So it's quite possible. Okay? So here you have coal, oil, gas, all fossil fuels with the 3 variants to estimate the MRI. And basically what it shows is that the trends, the patterns do not change, okay? And you just have more volatility with the price variant B, okay? Just have more volatility. But basically the pattern do not change. Okay? So what he's saying is that apparently the maximum EROI of oil has already been reached in the past. Okay, something around 70, 80 in the 1930s. The maximum EROI of gas has already been reached too. But for coal, maybe the maximum is now. Maybe it's not. Maybe it's in the future. So perhaps there is still net energy gains in the future for coal. Okay. Some sensitivity analysis with the energy intensity. Okay. Black is the first estimate. This is just for oil, with the energy intensity of the global economy. And the 2 over are with higher energy intensity. So it just translates the curve downward if you have a higher energy intensity. So it's quite logical. Okay. Comparison with Gagnon et al. So as I said, the only EROI estimate of global oil and gas was done by Gagnon et al. Between 1992 and 2006. So this is the estimate. Okay, and the 3 others are our estimates with the price-based approach. So you see that the correlation is pretty good in the end. Globally, we have the same trend, okay, increasing up to 1997 and then decreasing. But we have more volatility because we rely on prices. And something we can't really explain is why we are going in the opposite direction at this point. So if someone has an idea, I'm willing to take it.
We were going in oil.
Yeah, probably. So the prices.
Well, that's very, very low.
Yeah.
Below $10.
Yeah, but so the prices goes down, so our EROI goes up. Okay. Quite logical. Okay, so 15 minutes to finish. So the last question is that how we wanted to compare our price-based estimate with a theoretical model of the EROI. Okay. So this theoretical model of the EROI was produced by Dale et al. Okay. So basically what they say is that the EROI over time is a product of three things. Epsilon is a scaling factor. It's the maximum potential EROI with a perfect resource, perfect technology. And a G function, which is a technological component that increases the EROI over time. Okay? And H, which is a physical component, which decreases the EROI because when you deplete your resource, the quality is decreasing. So it's decreasing the EROI. Okay? And both functions, G and H, are a function of rho. Rho is the exploited resource ratio. So basically, it's the ratio of cumulative production to ultimately recoverable resource. Okay? So rho is 0 when you have not started to extract the resource. And rho is 1 when you have finished to extract the resource. Okay? So it's basically cumulative production on ultimately recoverable resources.
How is that different from H?
The two functions are a function of rho, okay? But, so this is the original model of Daily Hall, okay? So this is the technological component, G. So basically, here you have not started to exploit the resource. Here you have finished to exploit the resource, okay? Technology will improve your energy, your EROI, so it will improve the efficiency with which you extract the resource, okay? But there is also a physical component. You are extracting the resource, and the EROI is decreasing because you first extract the good resources before turning to lower quality resources, okay? So if you do epsilon times H times G, you have an EROI profile, okay, over time. So this is the combination. So this is the theoretical model. But in the original model of Daily Hall, the EROI could go under 1. Okay, this is the break-even threshold of 1. So it means that at the end, you continue to exploit the resource even if the EROI is inferior to 1, which is not really logical. It can make sense for a given year or for a few years, but once you see that your EROI is below 1, you will stop after a few years.
Another reason why they don't stop. Because it costs a lot of money to relaunch the rig.
Yeah.
So
Yeah.
you have thousands of rigs running in the rigs,
Yeah.
which are below the profitability.
Yeah, but the marginal cost, I mean, just the OPEX, it's little. So you can continue, but you don't drill anymore. Okay. So I've made two changes to the original theoretical model. First one that I've changed the function here so that it could be a sigmoid increasing function and not just only concave function. And I just add a limit here so that it could reach a limit and tends toward 1 here. Okay, so I made just 2 changes, really simple. And what we try to do is to calibrate this theoretical model on our price-based estimate. Okay? I do not have time to explain the methodology, but basically this is what the new model, theoretical model, will produce. So if you try, in fact, what I'm doing is that I'm trying to minimize the sum of error between the price-based estimate and the theoretical model. Okay? This is the modified version of the Daily Hall model. Okay, so this is for coal, this is for oil, this is for gas, and this is for all fossil fuels. And I have to speed up. So it just shows that the model, first of all, the theoretical model can reproduce historical estimates, and it kind of comforts also our estimates of the trend. I mean, it helps understanding the trend. So what it means is that the theoretical model is extra smooth, the price-based estimate is extra volatile, and the real physical EROI is somewhere between the two. Okay? So basically, the real physical EROI is following this trend with some volatility, but with a lower volatility than our price-based estimate. And then the big question we're asking, so what is going to happen after? Okay? And this is especially interesting for coal. Okay? So we took some value found in the literature about the amount of resource for coal, oil, and gas. Okay? And so this is the exploited ratio, you know, the raw thing between 0 and 1. So this is historical observation for oil, gas, all fossil fuels, and coal. And we have just calibrated a sigmoid increasing function with a few deviation range to test. I'm sorry, I'm going very quickly, but basically this is the result for the global EROI of coal. So our model, the new model, is saying that globally the EROI of coal is going to peak around 100, 110 in about 20 years. Okay, this is the EROI of oil. Okay, going down, continuing to decrease for gas and for fossil fuels. But of course, these estimates depend on the amount of that we have supposed underground. Okay, so just for coal, and it will be my last slide, we made a sensitivity analysis about the ultimately recoverable resources of coal. Okay, because you can find really different data in the literature. So a lot of data we found is that the amount of coal underground that will be ever recovered by human is about 100,000 exajoule. And we also find sometimes really lower estimate about 30 exajoule. Okay. So we just computed the model again. About the historical production, the match is the same, okay, because the calibration just changed the value of the parameters, but the calibration is the same. What's changed is the exploited resource ratio, okay, between 0 and 1, and hence it changed the future global EROI. But you see that even if you divide what you think is the amount of coal underground, if you divide it by 3, basically this is what the EROI of coal is going to follow with the low estimate of coal underground. This is what's happening with the high estimate of coal. So it's pretty consistent. Even if you don't really know what is the amount of coal underground, the trend is the same. Okay, basically the peak is just delayed if you think there is more coal. Okay, and the EROI peak is just a little higher, but not so much. Okay. So conclusion. We have had to rely on a price-based approach to estimate what we call yearly EROI of coal, oil, and gas from the beginning of the reported production to 2011. Okay, we could not make the same kind of methodology as what was shown yesterday for PV. Okay, we brought some amendment to the theoretical model of daily oil. Okay, what we think is that the past real physical EROI are probably somewhere between our extra smooth estimate of the theoretical model and between the more volatile price-based estimate. But overall, we suggest something that has been hypothesized a number of times, but never really assessed, that indeed the maximum EROI of oil and gas have been reached. Okay, they are in the past. And now the trend is only declining. But for coal, one of the new results that we have never seen in our study is that the EROI of coal can continue to increase. Not so much, but there is still gains coming from technological improvement. And we say that it will be, the EROI of coal will be about 110 and about in 20 or 40 years. what will be good to do for this study is that we have not made a difference between conventional fossil fuel and unconventional. And now that we are relying heavily on tight oil, on shale gas, shale oil, we have not made a difference between the two. So maybe the maximum EROI of oil, of conventional oil is past, but maybe the maximum EROI of tight oil is still in the future. I don't think so, but maybe. So there is still plenty of work. And thank you. And if you have questions, do not hesitate.